Greetings, welcome to lecture number 30 on basic circuit theory. I am Razavi. Today we will continue to look at the lossy parallel LC tank and try to quantify its behavior for different cases. We will see that there are actually three possibilities for the response of the circuit to the initial condition on the capacitor, and based on those we will arrive at the concepts of overdamped, critically damped, and underdamped cases. And we'll see that these actually are very interesting, and they are not just related to circuit theory. They can be also invoked in many different applications, such as mechanical systems, biological systems, social systems, etc. Now, before we go there, let's take a look at what we covered last time. We said that if we have a simple ideal LC tank like this, which is released with an initial voltage on the capacitor and no current through the inductor, just for simplicity, we saw that it satisfies this second order differential equation. We call it a second order system. And we have two initial conditions, a voltage here, no current here. So we can solve this differential equation by writing its characteristic equation and finding the S values from that second order equation here. And we saw that this just gives us two imaginary values, and that translated to a simple cosine for the waveform that we measure across this tank. So the cosine has a peak amplitude of V0, which is the same as the initial condition on the capacitor. And it has a radian frequency 1 over root L1C1, or a period equal to 2 pi times square root of L1C1. So we see that the period of the oscillation is a property of the circuit itself. The amplitude of the oscillation is a property of the initial condition that we place on the capacitor or in the inductor. All right, but then this is a very idealized situation in that there are no loss mechanisms included here. In practice, for example, if you build an inductor, what happens? This wire has some resistance, right? So there will be some loss. As the energy reciprocates between these two, some of it is lost in the form of heat through resistance. So a simple way of modeling that effect is to place a resistor here in parallel with these two. So we call this a lossy LC tank. And we would like to see what exactly happens, again, if we release it with an initial voltage on the cap and no current through the inductor. So we wrote the KCL at this node, and we saw that the differential equation came out to be like this when we added these three currents. And then we can write the characteristic equation for this result as shown here. So we see that it's a binomial, it's a polynomial of second order, and it has two roots. So the two roots of this can be expressed as shown here. Now, what we decided was that if the roots were real, they would have to be negative. That's what we discussed last time. And that's necessary because we would like all the responses in the system to decay and not grow, because we have these exponentials. So we'll talk about those more today, but this is the result that we got last time for the roots of this characteristic equation. And based on what's happening under the square root, whether it's positive or zero or negative, we end up with three types of responses for this output voltage. So let's go ahead and delve into that today and see what we can do. So we'll talk about the lossy LC tank. We saw 2 lectures ago that the three responses that we would expect for a second order linear differential equation were of this form, depending on the situation, right? So it could be 2 exponentials, it could be 1 exponential, another exponential multiplied by t, by a ramp, or it could be a cosine and a sine that have an exponential envelope. So just depending on the roots of the characteristic polynomial, we end up with one of these three cases. Okay, so here's our simple circuit, C1, initial condition of V0, then we have our inductor, we have our resistor, and we have our output voltage here. Okay, and we said that the differential equation governing the circuit can be written as follows. I can write it like this by simply keeping this coefficient to be 1. So then I have 1 over R1 C1 dV out over dt plus 1 over L1 C1 V out equals 0, right? And this differential equation comes with two initial conditions, right? We need two. And one is this voltage and one is this current. So we say V out at time 0 plus is V0. This voltage is the same as the voltage on the cap. And then the current through the inductor, IL1, at time 0 plus is 0. Now this is just in our example. In general, it doesn't have to be 0, but just for simplicity for now, we assume it's 0. So we solve this differential equation with these two initial conditions. To solve this differential equation, first we write its characteristic equation. Based on the results of that, we decide which one of these we should go with. And then all that's left are A1 and A2. And those can be obtained by enforcing these two initial conditions on the V out equation that we have obtained. So let's do that step by step and see what happens. Okay, so first we write the characteristic equation. So we have S squared plus 1 over R1 C1S plus 1 equals 0. And that gives us two values for S. So let's say S1 is equal to minus 1 over 2R1C1 minus, so we take this minus B plus minus B squared minus 4AC. So 1 over R1 squared C1 squared minus 4 over L1 C1. Actually, I need a factor of 1/2 here. So what I'm doing is the factor of 1/2 here. So remember that this gets divided by 2a. In this case, it would be just 2. So I just put that 2 here and here rather than a big denominator here. Okay, so this is one root. The other root has only a plus here instead of a minus. So let's do that. It's good to separate these two because in some discussions, we do need to distinguish between S1 and S2. So here's 1 over R1 squared, C1 squared minus 4 over L1 C1. So far so good? Okay, so these are the two roots of the characteristic polynomial. And we can make a number of observations about this result, about everything that we have seen so far, before we go and consider these three cases. All right? Okay, so let's make some observations. So, the first observations. So we say the circuit has an order of 2. It's a second order circuit. What does it mean? It means that the differential equation describing the behavior of the circuit is of second order. We can also see that because we have two different storage elements. One is a capacitor with an inductor. Each of these is governed by some sort of differential or integral equation. So when we have two of them, we get a second order system. All right. So observation number 2. Let's see here. Okay, so what we will do eventually is we will write V out in terms of this or this or this, right? And then we go ahead and enforce the two initial conditions to find A1 and A2. So for this one, it's not that hard. So V out at 0 plus is V0. So I go here and, for example, plug in 0 plus here, and I get A1 plus A2 equals V0. That's easy. But this part is a little tricky. I have the current of the inductor at 0 plus. But when I solve this equation, I don't have the current of the inductor yet. I have only V out. So somehow I have to relate V out near time 0 to the current through the inductor near time 0. Because that's what I have, but that's what I get. So let's work on that a little bit and see if we can create an equation for V out at 0 plus that captures this piece of information. The current through the inductor is 0. All right? So we say at t equals 0 plus, what can we say? All right, so let's go here and see. How much is this current, how much is this current, and how much is this current, right? So in a sense, I'm writing this differential equation in a very special case right at 0 plus, because I know something about the circuit at 0 plus, and that's this. Okay, so this current is 0 at time 0 plus. So what that means is that this current and this current have to add up to 0. How much is this current? V out over R1. How much is V out at 0 plus? It's V0, the voltage on the capacitor. So the current through the resistor is V0 over R1. All right. How much is the current through the capacitor? Well, C dV out over dt at time 0 plus. These have to be 0, right? The current to the capacitor, C dV over dt, and the current to the resistor, they're going in the opposite directions, they have to add up to 0. So this says something interesting. It says that dV out over dt at a time 0 plus, right, is equal to, we just bring this to the other side, we have minus V0 over R1 C1. So that's a good equation to have, because once I decide which one of these cases is valid for V out, then I can go find the derivative of V out, evaluate at time 0, equate to minus V0 over R1 C1. That will give me one equation in terms of A1 and A2. Then I have another equation for this case in terms of A1 and A2. Then I can find A1 and A2. Okay, so that's the second observation. So third observation. Let's see here. Okay, so what is the unit of S1 and S2? What dimension or unit do we expect here? Well, it's easy to see, because I see that this term is 1 over time. RC is a time constant, right? So it's 1 over time. So the dimension of these S values is 1 over time. So we say it's 1 over time. And sometimes you might say 1 over time is also frequency, right? So you can even call it frequency. But for now, we don't worry about that. We just think of it as 1 over time. All right. Okay, so that means that the larger the magnitude of S is, okay, suppose S is real, right? So suppose S is real, this whole thing is real. So the larger its magnitude, its absolute value is, the smaller the corresponding time is. All right? So if you just look at this term here, it's simpler to understand. The larger this absolute value here is, it means that the smaller RC is, right? So that means the time constant representing this value becomes smaller if this absolute value is larger. Now, at this point, this seems rather abstract and not very useful, but we will see actually that it's quite useful later. Okay, so at this point, we just want to remember that S1 and S2 have a unit of 1/second, or a dimension of 1/time. All right, one more observation. So, what we can say here is that the exponentials in all three cases decay. Does it make sense? Okay, so let's see. In the first case, we said that this case arises when S1 and S2 are real and unequal. All right? Okay, so, and we said that if they are real and unequal, they are both negative. If they're both negative, both of these exponentials decay, so we're set. How about this case? Same situation, right? Because again, we have this solution is valid when this square root is 0. So we see that again we have a minus here. So this has a negative power. It's a negative power multiplied by t. So that guarantees that both of these die away, right? So the net result eventually goes to 0. How about here? Okay, so remember that alpha was this part, right? So if alpha itself is negative, and it's guaranteed to be negative all the time, and then that means that this exponential and this exponential always decay. And they prevail. So this cosine swings between 0 and -1 plus 1, this one too, but these quickly go towards 0. So the final response here also goes towards 0. So the important result from this observation number 4 is that the V out always goes to 0, right? Regardless of what type of solution we have, regardless of how we choose the values in the circuit, we always go to 0 if we wait until time infinity. And again, that makes sense because we said that the exponentials cannot have a positive power because that would mean that they are growing with time, and that would mean V out goes to infinity, which doesn't make sense because the energy of the capacitor would be infinity. Okay, so now with these observations, we are ready to go and consider the 3 cases for the circuit. Let me make sure I haven't forgotten anything else. All right, so let's go ahead and consider case number 1. So we'll call this case 1, 2, 3, just as a number. So we'll go ahead and look at case number 1. Okay, so the way I distinguish case number 1 from the other 2 is that this overall term under the square root is positive, right? So what we have is 1 over R1 squared, C1 squared minus 4 over L1 C1 is greater than 0. So this tells us that this overall root is real, and these 2 roots are unequal because we have a negative here, we have a positive here. Okay, we'll write this in a simpler form because it's easier to remember. So you can write this as follows. You can say R1 is less than 1 over 2 root L1 over C1. Okay, just cross multiply and simplify, you'll get this. So this means that if R1 is small enough, right, R1 has to be smaller than a certain amount. If R1 is small enough, we have this solution. All right, okay. So then that means that our solution looks like this. V out is equal to A1 e to the S1t plus A2 e to the S2t. S1 and S2 are known, right? The values are known. We just have to find A1 and A2. Now we know that S1 and S2 are negative, as we explained last time. Okay, so how do we find A1 and A2? We always go back to our initial conditions and enforce those. Now we actually have a better situation we have this, and instead of this, we have this, right? We're going to use this one and this one to find A1 and A2. So let's go ahead and enforce this. It says that V out at time 0 plus should be equal to V0. So we're looking for two equations. So at time 0 plus, this is A1 plus A2. So A1 plus A2 is equal to V0. That's one equation for A1 and A2. We need one more. So we're going to enforce this one. So we say at 0 plus, the derivative of the output voltage has to satisfy this equation. What's the derivative of this? So let's write it out. We have A1S1, A1S1. The exponential is equal to 1 at 0 plus, so that goes away, plus A2S2. A2S2, the exponential is 1 at time 0 plus. This has to be equal to minus V0 over R1C1. All right, so that is the second equation. So we just go ahead and solve these two and we find A1 and A2, right? I won't bother with the details, so I just say that from these two, we can find A1 and A2. Okay? All right, so let's take a step back and see what has happened. Assuming that R1 is small enough so that we satisfy this condition, we have two exponentials as our response. We know that S1 and S2 are real, they are unequal, and they're both negative, as we talked about last time. So both of these exponentials decay, and each of them has some value, A1, which can be found from these equations. So let's try to sketch V out as a function of time. So here's what's happening. So we say V out as a function of time. Okay, so at time 0, how much is V out? Well, it's V0, right? V out is the voltage on the cap. So A1 plus A2 add up to V0. So we start at V0. And then we have two exponentials that both of which are decaying, right? So we expect that the net result should be decaying and should be going towards 0. So something like this maybe, right? Put a question mark here for now. So we have two exponentials, they're both decaying, so the net result should be something that decays. That makes sense. What we are sure about is this point and this point, right? We know that at time infinity we have to be at 0. Now how it gets from here to here, well, we have to see. Okay, so somewhat qualitatively speaking, that's our vision about the output voltage waveform when we have this condition. R1 is small enough, right, to satisfy this condition. But this is not quite correct, so we have to see why. All right, so let's go ahead and calculate or try to plot the current through the inductor as a function of time. And that will tell us right away that something is wrong with this drawing. All right? Okay. So I would like to do this. I would like to draw the current through the inductor. So we'll call it IL1. The current through the inductor as a function of time. Again, we're just sketching things, right? How much is the current at time 0 plus? It's 0, right? The current through the inductor cannot jump, so it's 0. How much is the current at time infinity? Also 0. At time infinity, this voltage is 0. All the currents have voltages have stabilized. They're no longer changing. So this inductor has 0 current through it. So over here, we have 0 current. So obviously, somewhere in between these two, IL has to reach a peak, right? So it has to go do something like this and then come back. Now exactly what it does, we don't know. But certainly, it has to go from 0 to some amount and come back to 0. All right? Okay. Now, whether it just goes like this, whether it goes like this, we don't know, and that's okay. For now, we'll just live with it. Now, you can see that this picture and this picture are not consistent. Why? Well, do we have an equation for IL1, the current through the inductor? Yes, the current through an inductor is given by L1, actually not L1, 1 over L1, let's see here, 1 over L1, integral of the voltage across it, right? Remember, the voltage across an inductor is L di over dt. So the current is integral of V, then divided by L. So that's integral of, sorry, I don't have room here. Just have to go down to here and say it's 1 over L1 integral of V out dt. Right? You want the current through an inductor, we take the voltage integrated with respect to time and divided by L1. All right, so if I look at this, knowing that, or assuming that V out has this shape, I realize that these two don't agree. Why? Okay, so this equation says to find the current, start integrating V out. Find the area under the V out curve and just move forward. So for example, if I want to find IL1 at this point in time, what I have to do is I have to go and find this area. Find this area, right, up to this time, and then divide by L1, right? Okay, so that's fine. But then if I keep integrating this area, you can see that the area under this curve increases monotonically, which says that the current through the inductor, meaning this integral, also has to increase monotonically. But that's not true. You see that the current goes up and it comes down. How could the area under this curve at some point come down? In fact, how could the area that under this curve go back to 0? You see, that's not possible. From another perspective, you can say that this is the derivative of this, right? Proportional to the derivative of this. But we see that the derivative of this is positive here, negative here, whereas this is always positive, right? It's always above 0. So these two do not agree. So how do we make them agree? Well, it's pretty simple. What we have to do is the following. So let's go to red. This voltage cannot go monotonically to 0. It has to go like this. Actually, all right, so what happens is that now you can see that the area is positive up to here, and that corresponds to this peak. You can see my times are not aligned, but that corresponds to this peak. And then beyond that, the area is negative, so it begins to cancel that positive area, and the output begins to fall. So when we go to time infinity, if you add up all of this area, it's equal to this area, and then everything makes sense. So the output voltage, even in this simple case, has to come down, go below 0, and then come back and then approach 0. All right, that's what the shape that this response would require. All right, there's always a little dip here before we go back to 0. Okay. All right, so now at this point, you are probably asking something profound that has been in the back of your mind. Last time when we discussed the behavior of this ideal LC circuit, we saw that it's a nice, simple cosine, right? And then we said if we introduce a resistance here, that resistance begins to dissipate some of the energy that is stored on the capacitor. So what we would expect is that this sinusoid doesn't want to keep its amplitude. It will gradually decay and it will die away. But what I saw here is nothing related to sinusoids, right? You can't see any sinusoid here. It's just a simple, sort of boring waveform. So what happened? Well, it depends on the value of R1, and it depends on the conditions that we are facing here. So as we will see in a moment, yes, we could see that decaying sinusoid only in this case, if R1 is actually greater than this value. But if R1 is less than this value, we don't see that. We see a little bit of dip here, but we don't see any sort of oscillation, decaying oscillation in the response. Okay, so this response is called an overdamped response. So we call this overdamped. And the term here really means this. We saw that this circuit without the resistance was oscillating, and we didn't like that. So we decided to dampen that. This is similar to, for example, you're in a car, and the car is driving, and the suspension is very bouncy. Every time you go over a pothole, the car goes like this, right? So we installed some dampers inside the car so that when you go over a pothole, it just very simply and smoothly makes a change, as opposed to bouncing up and down several times. So this resistor was placed here to reduce that oscillatory behavior. And by dampening that oscillatory behavior, we sort of get rid of it. And you can see here that we don't really have much of an oscillation. But we have done too much of dampening, and that's what we call an overdamped response. Okay? All right. So with that, now we are ready to go and look at the next type of response. But I also wanted to mention something quickly here, just in case you are curious. So why does it happen like this anyway, right? So if you have A1 times this, A2 times this, why is that the sum of these two actually goes negative and then comes back to 0? So here's the reason. So we say interesting point. Now you can show, if you go through the calculations and find A1 and A2, you can show that A1 is positive and A2 is negative. Okay? You can also show that that e to the S1t, S1 being this guy with a negative sign here, is a fast exponential, meaning it decays fast, whereas e to the S2t, meaning this one here, is a slow exponential. You made a mistake here. Exponential, so exponential. So let me illustrate what that means. So what we have is really the following. We have, as a function of time, A1 e to the S1t. This is a positive exponential, and it decays fast. So it looks like this. So A1 e to the S, this is A1 e to the S1t. Okay, A1 e to the S1t. A2 e to the S2t, on the other hand, is negative, because A2 is negative, and it's slow. So what that means is that it goes like this. So that's A2, and this is A2 e to the S2t. All right? So what happens is that now that we combine these two, what we see is that we have this dip, and then it takes, and it slowly approaches final value. As you can see, as we go to longer time frames, this has gone away, it's close to 0, so this one dominates, right? So whereas at a very short time scales, this one dominates because it's changing fast. So around here, we are following this guy. Around here, we are following this guy. And then in the middle, we have to have this little dip here. All right? Okay, so that's the reason for that dip. All right, very good. So now we are ready to go to case number 2. Case number 2 means that the response is of this form, and that happens if this term under the square root is 0, so that the two roots become equal. So we saw that if the roots are equal, the response has to be an exponential plus the same exponential times a ramp. So let's try to do that here. So we'll say case 2. So we have in this case we have an equality here. So R1 is chosen to give us this response, L1C1, and that means that V out is now equal to A1 e to the S1t plus A2t e to the S1t. We have only one root, so we just call it S1. All right? Okay. So S1 is known. That's just minus 1 over 2 R1C1. So we know that. We just need to find A1 and A2. 2R1C1. And we need to find A1 and A2. Okay. So again, we enforce this condition and this condition. So we have A1 plus A2. Actually, no. So at time 0, what we see is that at time 0, this is 0, we just have A1. So A1 has to be equal to V0, according to this equation here. So equal to V0. And then we have to take the derivative of this guy and equate it to minus V0 over R1C1. Derivative of this would be A1 S1 plus the derivative of this, which is 1, and then this is calculated at time 0, so that's plus A2. And then we have the derivative of this times t, and that's 0 at time 0 anyway, so that's gone. So this has to be equal to 0. So with those two, we can find A1 and A2. A1 is V0, and A2 is just obtained from here. Okay, so we can find the complete solution to the system. All right, so this case is what we call a critically damped system. So this response is called critically damped. This was called overdamped. This is called critically damped. What's the difference? If I look at the waveforms, how can I tell whether one is true or the other? All right, so we have to draw this very carefully. For that, I will go to the next page to show you how overdamped and critically damped look different. So here's V out as a function of time. Of course, they both start at V0, and they both go to 0, and they both have to have a dip, right? They go like this. So this is the case of overdamped, just comparatively speaking. So this is overdamped. If we have a critically damped situation, then it looks like this. So we start from here, and it comes down, and it approaches 0 faster. So this is called critically damped. So we see that in the case of critical damped, for example, in our circuit, when R1 is equal to 1/2 of square root of L1 over C1, the response is faster. It gets to its final destination more quickly than the case of overdamped, right? So in many systems, mechanical systems, electrical systems, social systems, we would like to have a critically damped response so that we can get to the final result as quickly as possible. All right? So that's what we call critically damped. Of course, this drawing is only relatively qualitative. If you have numbers, you can plug in and try to draw it carefully so that we can compare these two. But generally speaking, that's what we would expect. Okay, let's see. let's go to case number 3 and see what we would expect in that situation. So case number 3. So in this case, we have R1 is greater than 1/2 of root of L1 over C1. And this means that the term under the square root is negative, which makes the roots complex, right? The overall roots of the characteristic polynomial. So we say roots are complex. So when they are complex, we're going to write them in this form. So we say S12 is equal to minus 1 over 2R1C1 minus 1/2 J square root of 4 over L1C1 minus 1 over R1 squared C1 squared. I just swap these two under the square root so that I can factor out square root of minus 1, and square root of minus 1 is J, so that's what we have. So this is our complex, the two complex roots of this system. All right, and we said that in this case, the response is of the form of a cosine and a sine that have these decaying exponentials. So we said, let's call this value here, alpha, and we call this value here omega 1. Okay? And then we say our response, V out of t is equal to a1, which we don't know yet, e to the alpha t cosine of omega 1t, omega 1 is this number here, plus a2 e to the alpha t sine of omega 1t. All right? So what does this look like? We have these decaying exponentials. Alpha is negative, so it has to, these exponentials have to die away. And they prevail over the cosine and the sine. And then we have cosine and sine. So the result will look like a periodic sine or cosine that's dying away. So our expectation is this, that V out as a function of time begins with an amplitude of V0, as always, that's the voltage on the cap, and then starts dying, but because the system is not well behaved, it actually does this before it dies away. And this has an exponential envelope here, given by this term here, e to the alpha t. So now you can begin to see the resemblance between this response and the response that we saw for the ideal LC tank, right? So for the ideal LC tank, we saw that without any resistance, we had this perfectly periodic waveform. It never decayed, it never died away. But in the case of a lossy circuit, when R1 is there, and R1 is large enough, right? When R1 is large enough, you can see that R1 has to be large enough, and then the circuit does this, right? So it has that sinusoidal behavior, but it's decaying because in every cycle we lose some of the capacitor energy to the resistor in the form of heat. So eventually everything goes to 0. Okay, so this is what we call an underdamped response. All right, underdamped, again, like the car suspension mechanism, right? So you're going over a pothole and it goes like this for a while before it settles. So that's like this, right? It oscillates for a while before it settles. That means that the suspension of the car is not very well damped, so it has this behavior. So in many systems we don't like this, right? Because it takes a while for it to settle. So we want to avoid this and approach the case of critically damped response. So as you can see, if you remember how the critically damped response looked like, or the overdamped, we had a dip, and then we came back towards 0. So the distinction between critically damped and underdamped is that in the case of underdamped, we go to this dip, but then we cross the 0 again, right? For overdamped and critically damped, we did not cross again. We stayed below 0. But as soon as we go to this situation, we have one more crossing here, and then more crossings and so on. But overall, that's what it looks like. Okay, all right. So we have the values for alpha and omega 1. We're good on that. What we need are the values of A1 and A2. And again, like before, so 2 initial conditions, right? So we say, let's set t to 0. This is 1, this is 1, this is 0. So A1 has to be equal to V0. So A1 has to be equal to V0. That's one condition. The other condition was take the derivative of the output, evaluate it at time 0 plus, and equate that to minus V0 over R1C1, right? So we have to calculate this dV out over dt at time 0 plus has to be equal to minus V0 over R1C1, as I derived on the previous page. Okay, so this is a little tedious. You have to take the derivative of this whole thing and equate to this value at time 0. I'll just leave that for you, but we can see that we can find A1 and A2 from these two equations. All right, so that's what we call the underdamped response. Okay, so these were the different types of responses that we get from the simple parallel RLC tank, and I will see you next time.